a frequency analysis for continuous time signals for which we have CTFT and CTFT, CTFS and CTFT, continuous time Fourier series and continuous time Fourier transform. Now we'll have frequency analysis of discrete time signals. What is the basic difference between the frequency analysis for continuous time and frequency analysis for discrete time signals? Okay. See, for continuous time periodic signals, we have Fourier series this possesses infinite number of components. Where 1 by Tp is the spacing between two components. Okay. Frequency range in continuous time signal extends from minus infinity to plus infinity. Whereas such things are not possible in discrete time signals. Okay. See, for discrete time, first of all we should know that discrete time signal is obtained from continuous time signal. Okay. So once it is obtained from continuous time signal, so that means we have sampled a continuous time signal to obtain a discrete time signal. Now, looking for the sampling frequency. According to the Nyquist criteria, sampling frequency to avoid aliasing should be at least twice the maximum frequency present in a signal. Okay. That means discrete time signals are unique in frequency range minus pi to plus pi, or we can say 0 to 2 pi. So period for frequency in frequency domain, the period for DTFT or DTFS is nothing but equal to 2 pi. Okay, then how many samples we can have? Suppose the period is n, then number of samples 2 pi by n. Okay, that means there can be at most n frequency component which can be present in a Fourier transform of a discrete time periodic signal. Similar thing happens between in discrete time for non-periodic signal also. We have DTFT. DTFT, though it is unique between 0 to 2 pi, though it is continuous, but it is unique. Okay. This is a basic difference between for the discrete time signal and the continuous time signal. For continuous time signal, frequency ranges minus infinity to plus infinity. For discrete time signal, frequency ranges from minus pi to plus pi or 0 to 2 pi. Okay. Now we'll see Fourier series for discrete time periodic signal. Okay. The analysis equation for Fourier series where we can find the coefficient Ck is equal to 1 by n, since the series is discrete, n equal to 0 to n minus 1 xn e to the power minus j 2 pi kn by n. Okay, whereas synthesis equation xn can be written as summation k tending to 0 to n minus 1 ck e to the power j 2 pi k n by n. Okay, therefore number of components in the period of xn is also equal to n, period of ck Fourier series is also equal to n. Okay, and write note the spectrum of signal xn is periodic with period n is a periodic sequence with period n. That means both time domain and frequency domain, the period is equal to n. Let's see some examples. The spectra of signal xn equal to cos pi n by 3 is. Now look at this. What is the period of this? N equal to 6. Omega naught by 2 pi equal to k by n. This implies pi by 3 into 2 pi equal to k by n. This implies n is equal to 6. Okay. Now f naught is equal to 1 by 6. I can use pk by formula 1 by 6 summation n tending to 0 to 5 xn e to the power minus j 2 pi k n by 6. Okay, where k value change from period of the value of k and value of n will have the same range 0, 1, 2, 3, 4 and 5. Okay. Now xn can be written as 1 by 2 e to the power j 2 pi n by 6 plus 1 by 2 e to the power minus j 2 pi n by 6. Okay. Now looking at the equation of xn equal to 1 by 2 e to the power j 2 pi n by 6 plus 1 by 2 e to the power minus j 2 pi n by 6. This corresponds to k equal to 1 and this corresponds to k equal to minus 1. K equal to minus 1 is also equal to k equal to 5. Okay. See, this is periodic with a period 6. Okay. So after every period 5, after every period of 6, the same pattern will repeat. So I can e to the power minus j 2 pi n by 6 is equal to e to the power j 2 pi 5 minus 6 by 6, which is equal to e to the power j 2 pi 5n by 6. Okay, so I've got the two components, one at k equal to 1, another one at k equal to 5. Remaining components C0 equal to C1 equal to C2 equal to C3. They all are 0, and C1 equal to 1 by 2, C2 equal to 1 by 2. Okay, in this way the spectra of the signal can be found. Now if I plot this on frequency domain, I can write 0, 1, 2, 3, 4, 5. At 1 I have 1 by 2. At 5 I have 1 by 2. Remaining everywhere it is 0. Okay, and this pattern repeats. Okay, another example in which again determine the spectra of xn is equal to 1, 1, 0, 0, period equal to 4. Very simple. Use the equation 1 by 4 summation n tending to 0 to 3 xn e to the power minus j 2 pi k n by 4. K can be 0, 1, 2 and 3. Substituting the value of k and solving this, I will get Ck is equal to 1 by 4 1 plus e to the power minus j pi k by 2. Okay, so I got C0 is equal to 1 by 2, C1 equal to 1 by 4, 1 minus j, C2 equal to 0, C3 is equal to 1 by 4, 1 plus j. Okay, for this I can write the magnitude spectra. Mod C0 equal to 1 by 2, mod C1 is equal to root 2 by 4, mod C2 is equal to 0, mod C3 again equal to root 2 by 4. Phase spectra, angle at C0 0, angle at C1 minus pi by 4, angle at C2 tan inverse 0 by 0 becomes undefined, angle at C3 pi by 4. Okay, this way the magnitude spectra and phase spectra are drawn. Now since they are discrete time and periodic signals, so definitely they possess a power density spectrum. Okay, power density spectrum Px can be written as 1 by n summation n tending to 0 to n minus 1 x of n whole square. Okay, in terms of Pk, I can write the power spectrum as Px is equal to summation to 0 to n minus 1 mod Ck square. Okay. Now some points to note. First point. Ck equal to C of k plus n. Periodic dt etc. That means discrete time Fourier series is periodic with period equal to n. Okay. Next property will be regarding the symmetry properties. So if this is true, then I can write mod C naught equal to mod Cn, mod C1 equal to C of n minus 1, C of n by 2 equal to C of n by 2. Okay. If n is even, otherwise if n is odd, then definitely C of n minus 1 by 2 is equal to C of n plus 1 by 2. Okay. Now finding the dtfs for discrete time periodic square wave signal. It looks like this. I have n components placed here. Okay. L to n. Let each one is having amplitude A. Then again like this. Okay. Minus n. This is 0 point. This is a discrete time periodic square wave signal. For this, if I want to find the dtfs, I can write simply 1 by n summation n tending to 0 to n minus 1 n e to the power minus j 2 pi k n by n. Okay. So again writing the values, n equal to 0 to L minus 1, because up to L minus 1 only point it is not equal to 0. At remaining point it is equal to 0. Okay. K values varying from 0, 1 dot up to n minus 1. Then solving this, I can write my Ck is equal to KL by n of k equal to 0 plus n plus minus 2n, and it is equal to k by n e to the power minus j pi k L minus 1 oblique n sin pi k L by n by sin pi k by n. Okay. If k is not among these values, for other values of, okay, so this way the DTFS coefficient can be defined, can be found for a periodic square wave. Similarly, the power density spectrum is nothing but the square of the DTFS. So power density spectrum, just square square ck square. Okay, squaring ck square, this term will get square and this full term will get square. Okay, now we will see dt ft, which is Fourier transform for discrete time periodic signals. Okay, directly writing the synthesis and analysis equation for this. Again, this is a periodic x of omega this is analysis equation. Synthesis equation is 1 upon 2 pi integral 2 pi x of omega e to the power j omega n d omega. X of omega is continuous with period equal to 2 pi. Okay, so this is also a periodic, but here the number of frequency components are infinite between a period because it is a continuous. Okay, example, find DTFT for xn equal to a to the power n un, where mod a is lesser than 1. Okay, mod a is lesser than 1. So first we have to see whether xn is convergent or not. Xn is convergent, then definitely DTFT will exist for this, because we have seen the Dirichlet's conditions for Fourier transforms in continuous time domain, where the integral should be absolutely integral. Okay, there the condition is in CTFT, the condition is minus infinity to infinity xt dt should be lesser than 0. That means it is absolutely integrable. Here in DTFT, summation n tending to minus infinity to infinity mod xn should be lesser than infinity. Okay, so if we see summation n tending to 0 to infinity, it equal to 1 upon 1 minus mod a, which is lesser than infinity. Okay, because the value of a is lying between minus 1 and plus 1. Now, value of a is not equal to 1. Okay, value of a lie between minus 1 and plus 1. So it is absolutely summable. So once it is absolutely summable, I can use the formula is equal to 1 upon 1 minus a e to the power minus j omega. Okay, so this is a DTFT for given signal a to the power n un. With this, we finish the introduction of all the CTFS, DTFS, TTFT and CTFT for the signals. Now we will look into some more properties of DTFT, because DTFT is important as per this is more practical. Okay, generally the practical signal exists in nature are of discrete type and non-periodic signals. So we will take up more properties of this. The properties are similar to other type of Fourier analysis tools. Okay, but the important is DTFT. We will take up the symmetry properties and general properties for DTFT. Okay.